Oh, and there we go. All right. Well, guys, here you go. Today is the day that I told you not to miss. That's why Matt's here as our special guest, because you're gone tomorrow, right? So we thought we'd invite him along for the ride. So guys, let me explain to you what we are about to do, because if you understand the process, you'll be more successful. So guys, today we are going to learn about probably what has the potential to be one of the most interesting, intriguing, and yet confusing things you'll ever learn in your high school career. Now guys, here's the problem, and I don't say this pretentiously, but I'm just going to lay it out there. I am really good at teaching this. Actually, I may be a little bit too good at teaching this, because the problem is when I teach this to you, you're going to go, I get that. That's easy. What's the big deal? Just a number. I understand. That's no big, I'm okay. And then the problem is you get all cocky and you find out that this concept is named after a guy named Avogadro, which sounds a lot like avocado, and that's really hard to get past. And so every time we say the word Avogadro out loud, it's like avocado, and I watch the Super Bowl and I eat guacamole, and that's kind of, and it just, so guys, here's the problem. You guys understand this, right? Teaching is theater. I don't know if you get that or not, but guys, good teaching is theater. And what you're going to find out is this is going to get a little theatrical. Don't get distracted by the theater. Because guys, the best way to teach this is to create tension and to create resolution. And that's all about good theater. What you're about to find out is I'm going to spend 5 to 7 minutes with you explaining this big old enormous concept. And then about 5 minutes into this, I'm going to go, guys, I'm lying to you. And some of you are going to be disturbed because you're going to be like, dang, he's a good liar. And some of you are going to be confused because you have no idea why I'm lying to you, even though I told you right now I will be lying to you. But guys, the trick is this. I'm going to lie to you, blatant, bold-faced lies. And I'm going to lead you down this trail of lies to this dead end. And we're going to reach this point of crisis. And if you don't understand why we're at a point of crisis, you're not going to understand this concept. So we're going to stop and we're going to talk about it, and we're going to make sure you understand why we are all in crisis. And then you're going to find out that this concept is the solution to the problem. Then we're going to flesh out this concept. But guys, this concept is so abstract that the only way to help you appreciate the abstraction is through ridiculous analogy. And some of you are going to get distracted by that and avocados. And by the time it's time to really do the difficult math, you're going to be so far over here that you're going to come into this math and you're going to go, this is easy, I already know how to do this. And then you're going to get home to do your homework and you're going to go, oh, oops. So guys, understand that this is going to require focus. You're going to have to be on your toes. You're going to have to be nimble mentally, or you're going to miss the concept. You're going to get distracted. The math is going to fall apart, and you're going to build a very shaky foundation upon which you're going to really base the rest of this unit. So you ready to go? How was that for an introduction? I feel like I'm at like the Sundance Theater. Anyway, so guys, here's the idea. You remember the calendar, right? What does the rest of this unit look like? Lab, 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 right? What are we doing on Wednesday? A lab. What are we doing on Friday? A lab. So guys, what we're going to do is we are going to tie everything that you are about to learn to the lab that we're going to do on Wednesday and the last lab that we did, which was the tail end of the last unit. Do you remember that last lab? Here, let me show you just in case. Guys, the Precipitation Lab, remember this one where you did the yeses and the nos and then you wrote the balanced equations? Remember that? And if you remember, we had a a bunch of salts, but the idea was the salts got a positive and a negative ion and a positive and a negative ion. And what did they do when we mixed them together? traded partners, right? And if one of those new created salts was insoluble, what did it do? Precipitated. Do you remember all of that? Okay. So guys, with that as background in your notes, we need to go back another step, not back to the previous unit, but we need to go back 2 days. And guys, please in your notes, let's go back to formula mass, and please figure out the formula mass of table salt. And guys, understand that we are doing this in preparation for Wednesday's lab, which I will explain to you in just a moment. Now guys, you may remember that when we graded this homework last time, I encouraged you to show as little of your work as possible. And guys, that is still the case. If you can just do this in your calculator, great. Guys, do you remember what we're doing with how much data we're getting off the table? 1 decimal place, right? So sodium would then be 23.0. Watch out for chlorine because it doesn't round to 0.0. And then guys, come up with a number. Did y'all get a number? Not yet? Yeah, maybe? Sodium, chlorine. So here, guys, it looks like this. You, of course, didn't need to write all this down. I hope you didn't write all this down. In table salt, there's 1 sodium and 1 chlorine. And remember, guys, this isn't a molecule, right? It's not right to say a molecule of table salt because it's ionic. So it would be a formula unit. And so, guys, for 1 formula unit, same as molecule, because, guys, you remember, right, that salt looks like this, that it doesn't exist as molecules, it's a crystal, so we're talking about NaCl. So in 1 formula unit of salt, 1 Na, 1 Cl, 23 and 35, you okay with 58.5? Okay. So, guys, why did I have you do that for table salt? And so just play along. So here's what's going to happen. On Wednesday, as you saw in the calendar, we're going to lab. And guys, here's what we're going to do. We are going to marry this stuff together with the precipitation lab. So hear this out. So in the precipitation lab, you know that you mix salts together, and if one of the products was insoluble, it precipitated. But guys, we did that qualitatively, right? You were just descriptive. You were going, yes, it precipitated, no, it didn't. Guys, what we're going to do on Wednesday is we are going to repeat the lab quantitatively. And here's how this is going to go. We're only going to do 1. I will give you a salt-salt combination that will precipitate. And so one of the subjects will be NaCl, table salt, and then the other one will be silver nitrate, AgNO3. And what you'll do is you will weigh out, well, first you'll figure out the mass of AgNO3, and we'll do that on Wednesday. But then what you'll do, guys, is you'll weigh out some salt, NaCl, and you'll weigh out some silver nitrate and you'll dissolve them in water. Then what you'll do is you'll mix them together and it will precipitate. The silver chloride is not soluble and it'll form this white chunky stuff inside the beaker where you mix them. And then, guys, we're going to separate the chunks from the liquid. How can we do that from what you learned in the salt and sand lab? Filter it. You're going to dump that through a filter and the solution will go through the filter and the silver chloride will collect in the filter. And then what you'll do is you'll dry it out and you'll weigh it and then we'll do some math to figure out a percent error. So guys, bottom line then is this. When you come in on Wednesday, you'll figure out the mass of silver nitrate just like you did sodium chloride and you will go into lab and you will weigh out 58.5 of salt and then whatever the mass of silver nitrate, you'll weigh that out, you'll dissolve it in water, you'll mix it together, you'll precipitate it, filter it, collect it, and weigh it again, and then we'll do a percent error. You got the idea? No, you don't. Because if you did, you would understand that I am lying to you. Because guys, what I just told you is impossible. You cannot carry out the lab that I just lied to you about. So guys, can we precipitate things? Sure. Can we dissolve salts in water? Absolutely. Can we filter precipitates? Yeah, we're going to, not on Wednesday, but absolutely. Guys, all of that is, we're going to do that. So where was the lie? Where was the impossibility? Where was the thing in my description of the lab that is impossible to do? Do you not see it? Go ahead, Lauren. No, we can, and we will. We're going to do this in March, but you can. We'll actually create, it won't be silver chloride precipitate. We do that in AP. But the silver is expensive. No, you absolutely can. We'll be filtering precipitates, no question. So guys, where was the lie? Where was the part of this that's impossible? Yeah. No, you can. Silver nitrate dissolves in water, and so does sodium chloride. Guys, go back to this idea, and it's on the board. How much salt did I tell you you were going to weigh out in lab? 58.5, right? You'll notice that I didn't put units on that because I was afraid that if I said the units out loud, somebody would pick up on it. So let's add units to it. Guys, 58.5 atomic mass units. What's the problem? Because you did all these calculations. You did a whole homework assignment on this, and you don't get it. Guys, how much salt is this? 1. Guys, it is 1. It is not 1 crystal. It is 1 salt. It is 1 sodium and 1 chlorine atom. What I told you to do in lab when I said go and weigh out 58.5 AMUs of salt is I told you to go weigh this much. 1 sodium and 1 chlorine. Because if you don't understand the problem, let me maybe offer it to you this way. And don't write this down, what is an atomic mass unit? It's the mass of a proton. Guys, it's this. It's 1.67 times 10 to the negative 24th grams. So when I told you to weigh out 58.5 atomic mass units of salt, multiplying this by this is how much salt I told you to go weigh in lab. Now guys, the $200 balances that you have at your lab tables weigh to 2 decimal places. The $3,000 balances that I use with my AP students weigh out to 4 decimal places. Guys, even the $3,000 balances can't even touch this. So you understand what that means, right? Your periodic tables are worthless to you. Because guys, what are the units of mass on your periodic tables? AMUs. All those little numbers in red are in AMUs. And guys, chemistry is a hands-on science. And so these masses are worthless to us because they are so small, they have absolutely no meaning to us. When we go figure out the mass of salt as 58.5 atomic mass units, it's worthless information to us because it is so stinking small that we can't use those numbers in lab in a meaningful way. Do you understand the problem? So what's the solution? And guys, the solution is this. Why is this number meaningless to us? Because it's so small. Why is it so small? Because it's the mass of 1 formula unit of salt. So if 1 formula unit of salt isn't enough for it to be meaningful to us, what do we do to fix the problem? Get more salt. You understand the idea behind that? Guys, don't write this down, but watch. So this is the idea. We have just said that 1, literally 1 NaCl has a very small mass. It's 58.5 atomic mass units, which is this in grams. And again, that is not enough mass. It's not enough salt for us to weigh it. And guys, this is where this gets a little ridiculous. Bear with me because this is cool. You ready? So guys, you understand the problem. That one doesn't weigh enough. So guys, if one doesn't weigh enough, what do? We get more. So guess how much more salt we're going to get? Wait for it, 12. I know, it's a little crazy. But guys, why did I pick 12? I picked 12 because 12 has a name. What's the name for 12? A dozen. So guys, if somebody came up to you in a dark alley and held a gun to your head and say, tell me the name of 12 or you're a goner. If you lose your life, you're an idiot. Because 12 is a dozen, right? 12's a dozen? You all know that. So guys, you ready? How much will 12 salts weigh? Will 12 weigh more than one? Yeah, how much more? 12 times more. You ready? I did the math. 702 AMUs. Whoa! 700! That's that in grams, though. Is that enough? That's not enough. So guys, let's take off the kid gloves. Obviously, 12, 13, 14, that's not enough salt. So how much salt do we need to make it a big enough pile that we can weigh it? How about this? 144. A dozen. Now, for those of you that buy rockets on the 4th and the 24th, you know that a dozen has a name. Actually, they still can't sell these in Utah, so you're about to out yourself as somebody that goes to Evanston for fireworks. All right, Ammon's nodding his head. So, hey.
Just real quick, I'm looking for a printer cable that kind of has a square end and a USB.
I've got lots, but yeah.
See you later.
Yeah. So guys, a dozen, right? Ammon, what's that called? Don't know. Does anyone know? It's a gross. Did you guys know that? The word gross means a dozen. So would you lose your life now in the dark alley on that one? So how many is a gross? 140, dozen, 140. So guys, a gross is 144. So what is that going to weigh? Well, 12 times this or 144 times that, 8,400. Look at it in grams. Still not enough. So guys, obviously we played that up a little bit, but this is where this gets cool. You ready? Obviously, this is going somewhere. We understand that playing these games by dozens and dozens of dozens isn't getting us close. But guys, the thing that we do understand is that groups can have names. 12 is a dozen, 144 is a gross. So now guys, check this out. How many salt formula units do we need to have enough so that we can functionally weigh them in lab? And there's an answer to the question, and it's not 12 and it's not 144. It is 602 septillion. That is this number, 6.02 times 10 to the 23rd. Now guys, that is how many salts so is 602 septillion going to weigh more? Yes. But guys, just like these groups have names, so does this. It's called a mole. Guys, a mole is a counting group. You can have a mole of eggs. You could make a really big omelet with a mole of eggs. Because guys, a mole is 602 septillion things. But it's just like a dozen, it's just more. So when somebody comes up to you in that dark alley and holds that gun to your head and says how many things are in a mole, a lot of you are going to lose your lives. Because you're not going to come up with 602 septillion because you think it's a chemistry thing. It's just a group. You can have 602 septillion of anything, just like you can have a dozen of anything, and that would be 12. But it's 602 septillion. But now, guys, if you're taking notes, stop and watch. This is the magic. Guys, will 602 septillion salts weigh more than 1 or 12 or 144? Yeah. How much more does it weigh? This much more. That's pretty cool. Do you see the connection? What's magic about that number 58.5? It's the same as one thing in AMUs. Guys, 602 septillion is exactly the number of things that you need to have that pile's mass in grams be exactly the same as the mass of one of them in AMUs. That is a powerful thought. And guess what? Now your periodic tables are no longer broken. Because guess what these numbers can also be in addition to AMUs? Grams. And if it's in grams, you said it right, but backwards, if these masses are in grams, we're no longer talking about individual atoms, we're talking about moles of atoms. So guys, for example, if you look at carbon, what's carbon's mass? 12. 12 what? Well, if it's one atom, it's 12 AMUs. But what if it's a mole, 602 septillion carbon atoms? It's 12 grams. Do you get it? That's a powerful idea. So let's start taking notes. So guys, this is called a mole. And a mole is a counting group, just like a dozen or a gross. But the magic of this counting group is it allows mass conversions directly from AMUs to grams. And guys, I know we made this connection, but the idea is this. This number in AMUs will be the same as a mole of those things in grams. All right, guys, you ready for the collective chuckle? Who came up with the idea? His name is Avogadro. Sounds like avocado. The only thing that could possibly make this worse is if I dressed up like a mole. And there are teachers in this district that do that. You can actually go online and from educational supply stores buy a human-sized mole costume to teach this. Well, again, teaching is theater, but for people that actually don't understand the concept, they think they can draw kids in by looking like a rodent. Okay, that frightens me that you went there, but that could be my ticket to retirement. Start a website. Hey, chemistry teacher, sick of dressing up like a rodent? Try an avocado. Good heavens. So guys, what is Avogadro's number? It is simply the number of things in a mole. If we knew the baker that came up with the idea that a dozen was 12, we could have named 12 after him or her. But guys, we know who came up with 602 septillion, and that's our friend Avogadro. So Avogadro's number is the number of things in a mole. Please don't write this down, but this is what it looks like written out. Guys, how many significant digits are in that ridiculously long number? 3, the 6, the trap 0, and the 2. All the rest of these are placeholding zeros, so putting that in scientific notation, it looks like this. 6.02 times 10 to the 23rd. Okay, so guys, now, all chuckling aside, here's the problem. We understand that this is a big number. Atoms are small. This number's got to be big in order to weigh that pile of atoms. But guys, the problem is this. How big is this? How big is 602 septillion? And I would propose to you that it's indescribably big. It almost gets into hyperbole. It's crazy big. But let's try. You obviously don't need to write any of these things down. But guys, how big is a mole? Well, guys, if you've got a mole of things, how many do you have? Some of you just died in the dark alleyway. If you've got a mole of things, how many do you have? 602 septillion. Okay, now guys, what about this? So, faster, like think iPhone 6, okay? So, faster computational things, you understand that your iPhone is in fact a computer that's a lot more capable than even the computers that got us to the moon. But guys, faster computers, reasonable, run at about 8 billion operations per second. So in 1 second, 1/1000, the processor chip inside of an iPhone can do about 8 billion things. So let's put that in context. How many people are on the planet currently? 7 to 8 billion. We're not quite sure. So how long would it take an iPhone to accurately count everybody on the planet? About a second, right? So here's the question. How long would it take that same computer at 8 billion operations per second to count up to Avogadro's number? Guesses? A year? Guys, think about that. A year at 1 billion things a second. A day? A week? Some of you are trying to do the dimensional analysis, which is the right way to solve this. And guys, if you do it right, the answer is 2.4 million years. Now guys, here's the problem. 2.4 million years is mind-boggling, but still not comprehensible. You can't remember yesterday. To try to wrap your head around 2.4 million years is beyond the scope of what we can do. So let's make this a little more reasonable. Guys, what about this? What if you have a mole of raindrops? How many raindrops do you have? 602 septillion. Guys, how large would the container need to be to contain 602 septillion raindrops? Well, let me start the conversation. Let's make it 100 feet across, a third of a football field. If we had a cylinder 100 feet across, this room is about 30 feet wide. If we had a cylinder 100 feet across, how tall would the cylinder be to hold a mole of raindrops? A mile? Guys, it would actually extend to the sun and back 140 times. We're talking about a fairly large number here, but the problem is we've never been to the sun, so we can't wrap our head around that. So let's try this one on for size. Guys, airsoft pellets, BBs. You have experience with these. They hurt. So, guys, what if you had a mole of airsoft pellets? How many do you have? 602 septillion. How big would the container need to be to contain 602 septillion airsoft pellets? To put this in that's 10,000 when it's full. How big a container? So, 602 septillion airsoft pellets, would they fill my sink? Yeah. Would they fill this room? Come on, guys. You say yes flippantly, but think about that. Think about this room full of airsoft pellets. Would it fill the field house? Easily. So guys, here's the problem. I did my best to come up with something that we could wrap our arms around or our minds around relative, because we can picture 100 feet wide, but to the sun and back, that makes no sense. So guys, this is the best I could come up with. How big does the container need to be in order to contain a mole of airsoft pellets? Well, we would have to turn the state of Utah into a Tupperware container. So we would have to put walls from Idaho to Wyoming to Colorado to the south to Nevada to all the way around. And guys, if we leveled the state of Utah, a mole of airsoft pellets would bury the state of Utah 253 feet deep. That's a lot of airsoft pellets. Let's do one more. Guys, let's bring this back to chemistry, shall we? So guys, what about this? How many things are in a mole? 602 septillion. Now, what if we have a mole of carbon atoms? How many do we have? 602 septillion. If they were raindrops, they would go to the sun 140 times and back. How big is a mole of carbon atoms? Right there. Because that's it. In this flask, there are 602 septillion carbon atoms. How do I know? Did I count them? That would take me 2.4 million years at 8 billion a second. Guys, if these carbon atoms were the size of airsoft pellets, how big would they be? State of Utah, 253 feet deep. Do you now appreciate how small atoms are? Remember blueberries in the grapefruit, the earth, the thingy? Yeah? Guys, they're bitty. So how did I know that there were 602 septillion carbon atoms in here? It weighs 12 grams. Right? That's why I drew your attention to carbon earlier. The mass of carbon is 12. 12 what? Well, one atom weighs 12 AMUs, but guys, one mole of atoms weighs 12 grams. So guys, all I had to do, and please don't write this down, all I had to do was leverage this relationship. If one carbon atom weighs 12 AMUs, then Avogadro's number of carbon atoms, which we call a mole, weighs 12 grams. But now, guys, watch this. If that's 1 mole of carbon, guess what this is? 2 moles of carbon. But now, guys, watch. What does 2 moles of carbon weigh? Think about it. If 1 mole weighs 12, 2 moles weighs 24. So the idea is this. If 1 mole weighs 12, then 2 of those weighs 24. Doesn't that make sense? Now, guys, is there 6.02 times 10 to the 23rd carbon atoms in here? How many are in here if it's 2 moles? Double that, right? So I did the math but didn't put it in very good scientific notation. It's 12.04 times 10 to the 23rd. It's 2 moles of carbon atoms, so it's double that. Do you get the idea? Now, guys, guess what? You just did all the dimensional analysis that you're going to do for the rest of this unit on the board right there. That's it. So when you get into the middle of this tonight and on Wednesday and on Friday and you go, I don't know what I'm doing. Guys, it's just this. All that we are going to do is convert moles into grams and moles into atoms and other types of particles. So guys, it's at this point that you need to grab this. This is going to become your guide but not your crutch because you will not have this on the test. But guys, make the connection. You ready? What's in the middle on the screen? Look at the green laser. What's on the middle of the screen? Moles. Put it in the middle of your chart. Guys, look. Moles are in the middle. Moles are in the middle. Just right here. Write the word mole. Now, guys, what was off to the left? Atoms, but we're going to call those particles. And what are particles? Particles are things like atoms or molecules or formula units. And then off to the right, we had mass, and mass is measured in grams. And then, guys, down beneath, this is sort of out of left field, we are also going to make conversions into gas volumes. Those will be measured in liters or decimeters cubed because those are our units for volume. So now, guys, let's talk conversions. And I'm just going to give them to you, and then I'll help you make the connection. When we want to go from moles to particles, we need Avogadro's number. When we want to go from moles to mass, we need the formula mass. That is why the first day of this unit, we calculated formula masses. And guys, I told you, you'd better get good at them. The reason is because you're going to be using them to make these conversions for the rest of the year. And then, guys, this one, just write it down. it turns out that a mole of gas has a fixed volume. If you have 602 septillion gas molecules, they will fill about 11 2-liter bottles. It's actually 22.4 liters. So if you have a mole of gas molecules, whether it's oxygen or hydrogen or helium or methane, doesn't matter, their volume will be about 22.4 liters. Okay. So now, guys, let me help you make the connection. You can't do this because you probably weren't taking notes because I told you not to, but let me show you. Look at what we've got. We've got particles, we've got moles, we've got mass. But, guys, let's go back to our previous screen, which looks like this. Notice what we've got. Atoms, which are particles, moles, and mass. And if we mentally slide that table up, you'll find that it matches moles, mass, and particles. And you will notice that to get from moles to mass, we need the formula mass, which in the case of carbon was 12. And when we want to go from moles to particles, we need Avogadro's number, which is right there. And guys, those are the conversions that we're going to be doing. And then later in the homework, you'll see we'll do the bottom conversion to liters of gas. So we're going to do 2 of these together right now. Guys, this is going to depend on my board working properly as an interactive tool. If it doesn't work, I'll go to the whiteboard and grab a pen. But here we go. You're going to want to write this down. What is the mass of 2.3 moles of NO2? That's okay, isn't it? Can you? Is it okay? Yeah, it's a really tight picture, but it's also a really small picture. But Hunter, is that okay? Like it's okay. Yeah, it's nice because it's such a clean, crisp image that even in a smaller font, I think it's a little more readable. So guys, what is the mass of 2.3 moles of NO2? How do you like my little pen case? Check it out. Oh! I know, right? Well, yeah, it actually is, because seldom does it work. Okay, so, guys, dimensional analysis. You told me when we graded homework you were money, so what's the first thing we do? We need a goal. Where does it go? The right-hand side. And I know these problems are new to you, and moles and things don't make a lot of sense, but contextually from reading the problem, what is our goal? Mass, grams. So, but guys, watch. This is important. We're going to go grams, but it's grams of NO2. That matters. You've got to not just write down grams, but grams of what? Now, where are we starting? Well, obviously, the information that we're given, which is 2. And guys, let me just tell you, one of the things I really can't do is draw dots for decimals. I'm going to have to do little X's for now and see if I can fix it. So 2.3, you ready for this? That's the abbreviation for mole. Pretty sad, right? Drop the E. 2.3 moles of NO2. Step 3, draw a line. That is the best that this thing has performed yet. Because I can't draw dots. It won't let me do decimal places. Okay, so guys, step back from this for a minute and look at where we're at. We're in moles. We want to be in grams, right? Now watch. Take that idea, we're in moles and we want to be in grams, and go to our table. And let's look. We are in moles and we want to be in grams. So as you reference your table that you have in front of you, what is the bridge between moles and grams? Formula mass, which you learned to calculate 2 homeworks ago. So guys, we're going to go here and here and here. And guys, let me show you a shortcut for this. We need the formula mass of NO2. Find nitrogen element number 7. What is its mass? 14. But wait a second. Up until now, we've said 1 decimal place. That is not the deal. This is the deal. Guys, watch. How many significant digits in 2.3? 2. That means that you have got to take 2 significant digits off the masses on the periodic table. But we will never go less than 1 decimal place. So we technically only need 14. But we will always add at least 1 decimal place. So nitrogen then is 14.0. And I'm just going to put it right there. Now, oxygen, 16.0, but we'll double it. So that is 32.0. Now we add those up and I get 46. So what does that mean? What does 1 mole of NO2 weigh? 46 grams. 1 molecule weighs 46 AMUs. 1 mole weighs 46 grams. So guys, what goes on the bottom? The 1 mole or the 46 grams? The 1 mole, so it cancels. So 1 mole of NO2 is 46.0 grams of NO2. Now guys, canceling, moles are gone. We're left with grams, so we're done. So we do the math, and we've got 2.3 times 46, and I get 105.8 grams, but that is disregarding significant digits. How many significant digits in 2.3? 2. How many significant digits in 46.0? 3. So we get 2, and to 2 significant digits, that would be 110 grams of NO2. It's disappointing. What do you think? Process okay? Questions? Let's do one more. Yeah, please. I did. Oxygen is 16, and when I doubled it, it became 32. Yeah, good point, and I did. We good? Go ahead.
I'm just kind of confused on what you were saying about taking oxygen.
Let's do another one and talk about it, but let me restate it again. The rule is this. Where you start tells you how many significant digits you need. In this case, we only need 2. But, and frankly, this is just the way I learned it in college, and it was just their thing, is you never go less than 1 decimal place. So if you want your answers to match mine in the key, we will go the number of significant digits here, but never less than 1 decimal place. Let's look at another example, and I think it'll make more sense. Okay? Okay, guys, try this one. How many molecules of water are contained in 25 grams of water? Guys, this is 25 grams of water. So the question that we're asking is, how many water molecules are in here? We're going to calculate it. So what are we solving for? Not AMUs. Molecule. And be careful, AMUs is a mass. We want to know how many molecules. So guys, how do we represent that? Just like this. We want to know how many H2Os. Now, how many H2Os are in what? Well, how many H2Os are in 25 grams of H2O? So now, guys, where are we starting? Grams. Where do we want to go? Molecules, which are what? Going back to your little T chart, molecules, which are where? Particles. So guys, keep that in your mind. Mass to particles. So guys, we want to go mass to particles. So we want to go, come on. We want to go mass to particles. So guys, now what we are talking about is a two-step conversion, because we're going to go mass to moles and then moles to particles. So what do we need in order to go mass to moles? The formula mass. And then how do we go moles to particles? 602 septillion. So we are going to take that idea and we are going to apply it to this process. So the first thing we need to do is we need to go mass to moles, and that requires the formula mass. Now guys, watch. How many significant digits in 25.0? 3. So now go to your periodic table and find hydrogen's mass to 3 significant digits. 1.01, right? Isn't it 1.08 something? Well, 1.007. So to 3 significant digits, that's 1.01, but there's 2 of them, so that would be 2.02. Then guys, oxygen is 16, and to 3 significant digits, that's 16.0. Now what do we get when we add those up? 18.02 grams is 1 mole. So what goes on the bottom, the grams or the mole? So it cancels the grams. So, oh boy. So 18.02 grams of H2O is 1 mole of H2O. So now we can cancel grams. But are we done? No, because we're not in particles. We're not in molecules. So now we need to go from moles to particles. And how many particles are in a mole? 602 septillion. So what goes on the bottom, the 1 mole or the 602 septillion? The 1 mole. So canceling 1 mole of water is 6.02 times 10 to the 23rd waters. Now our moles cancel and we're at our goal, so we do the math. And guys, if you're going to put Avogadro's number in your calculator by hitting the times and the 10 and the caret, shame on you, because I taught you better back in August. Relearn how to use your exponent key. So guys, 25 divided by 18.02. Don't multiply by the 1. Multiply that by 6.02 times 10 to the 23rd. Don't divide by the 1. And I get 8.3518 times 10 to the 23rd. And then looking at significant digits, guys, let's figure this out. How many in 25.0? 3. How many in 18.02? 4. How many in Avogadro's number? 3. And that is not perfect. It does limit significant digits. So we have 3 and 4 and 3, which gives us 3. So this would be 8.35 times 10 to the 23rd water molecules. Yeah? Right. It could be. And understand, if you wanted to cut this back to 3, that's totally fine. And you would be correct. But the rule is this. These masses can never limit significant digits, but you can have as many digits as you want in addition. So long as we figured this out to 4 significant digits and doing this, we may as well keep them. If you choose not to, you're not wrong. But the thing that will make you wrong is if this limits significant digits. Okay? Other questions, y'all? Okay, so we have about 15 minutes. Here's what we're going to do. You're going to grab your homework, and eventually you're going to do the whole assignment. But for right now, you are going to do every fourth problem. Which sounds a little crazy, but you're going to do 1 and 4. And so do number 1. Actually, you know what? No, that's right. You're going to do 1 and 4. So do every fourth problem, but do number 1 as well. So number 1, number 4, number 8, number 12, number 16, number 20. Guys, the reason that we're doing this is because these are grouped by problem type, and I want you to have the experience of seeing a lot of different types of problems. So do number 1, and then every problem divisible by 4. And guys, again, when you get stuck with these, but you understand eventually you'll do them all. But for now in class, do those so that you can get practice with these while you're around me. When you need help, please come and get with me tomorrow. Get an eye for pride, whatever you need to do. But guys, make sure you're getting help. So 15 minutes, dig in, let me know if I can help.